Hello everyone, welcome back. So today we'll start a new topic. We'll talk about air bearings and guideways. So now we understand that why friction is a problem and how it prevents us from achieving any accuracy or achieving higher repeatability. So definitely then non-contact type of bearings are very important. So we'll talk about air bearings and guideways. So, as we when we started, we talked about products, and if we see different kind of products today, the consumer products, the electronic products, all kind of gadgets we have at home in our offices. What we observe that they are very efficient, elegant, and at the same time very affordable, very cost effective. Yes, the size, the footprint, they are very small, small in size, but it's loaded with features. At the same time, the quality, reliability, and the performance they are is there. It's inbuilt, and we don't compromise on that. At the same time, when we are looking at the machines today, the systems, the instrumentations, the machines which enable us to produce these products today, they are very complex. They look very different. They are very precise and fast moving, and they can do the alignment and adjustment on the fly. And we have enabled creating features in the size of microns or even at the nanometer level. And that's how we are able to get these modern products, modern systems with so many capabilities. So one of the element when we look at all these products or machines and which enables us to produce these products with higher precision, what we understand and what we recognize that we cannot eliminate motions. There will be relative motion between the different components, different modules. Of course, there are different guideways, a lot of bearings surfaces we have, and if we check or look at those designs, what we realize, for instance, these machines. So we talk about this design, the V and flat, and what we also understand how exact constraint design principles or controlling degrees of freedom enable us to design this system to achieve higher repeatability, and at the same time we can avoid any kind of over constraints. So the machine tools, the systems, they have a V and flat, and we can recognize them in the older machines, and if they are meant to fabricate or manufacture precision components, this we can easily see and these features on those machines. As we move on, what we have realized that all the modern machines, when going for higher speeds and looking for robotics and automation application, now those guides are replaced by the linear guides, and of course they are uh, there is a sliding motion, but at the same time if we look at it closely, look at the construction, what we realize that they are recirculating balls inside, and it's just like ball bearings embedded inside the linear guides. So we can get a very good speed. Yes, with respect to the precision, there is a limitation. Of course, it's better than purely sliding bearings or sliding joints, what we can call it. And so, but still there is a physical contact, there is a friction involved, And what we studied, that wherever there is a friction involved, no matter how stiff is the structure, there will be associated virtual play, and that will be the limitation, that will be the positioning uncertainty we'll get because of the friction and the limited stiffness of the component. So, as long as there is some kind of physical contact, either sliding or rolling, we'll bound to have certain hysteresis, and therefore we have a virtual play. And if we want to get rid of those errors, we have to find ways where we can eliminate this kind of contact altogether. So, we look at some designs. So, and that's why we are talking about air bearing these days, and we'll cover air bearing linear stages or motion stages. So, it's two axis, what you can see here, and there are air bearings embedded, and that's how it works. There are orifices, so pressurized air is fed through, and then it passes through the bearing surface, and at the same time we have also, so we can combine vacuum and the pressurized air bearing in one module. So here there is no vacuum. And what we realize that there is no mechanical contact, and the air film what we have is of the order of 5 to 15 micron only. At the same time, these air bearing systems, since it works on air bearing film, so there is no hard contact, so we get a averaging effect, and it also eliminates errors because of that. And since there is no contact, there is no mechanical wear as well. For this kind of machines, we also want to have a yaw control. So, for instance, if you have this, so there are two linear guides on the either sides, two linear motors. So, we want to have that control, and therefore, we also need to have flexure bearings at the end so that it can adjust or it can rotate. There are direct drive, the linear motors are there. So, it's directly embedded on the linear guides. So, once energized, the magnets and the coil, so magnet will be stationary and the coil usually lighter, so it will be with the motion stage, and it can move freely. So, it's a direct drive, so there is no error associated with the transmission. And of course, there will be sensors there. And so, if we look at these designs, what is the key component what we have is the air bearing. So, another very good example is photolithography machines, and it's just a construction shown here. And of course, we have the projection lens and photo mask, and we shine a light, and then that will be shined on the wafer here through that projection lens, and this has to be moved at a very high speed, but very precisely. And what we realize that this wafer stays is having air bearings, so that there is no hysteresis involved and it can move very fast. The friction is not there, is almost negligible. And so, all these high end equipments and these machines, what we realize that the air bearings are the key components, and these are used to design different kind of guides and different kind of motion states, so that we can move quickly and precisely. So, of course, we'll concentrate more on air bearings, and later we'll be talking about how to build different kind of motion stages or guides using these air bearings. So what we realize here, there are different kind of air bearings. So yeah, we can classify it as aerostatic bearings also, because the loading, the bearing, the way it works is not because of the dynamic effect, but it's more like a static effect. So there is a pressurized air fed through the orifices, and then we create a pressure under the bearing surface, and that's how it's able to support the load. So these are different kind of grooves you can see. It's one good thing is it can be a separate element also, but at the same time these kind of designs can be embedded, can be um, we can make different kind of patterns, groups on the surface itself, and we can get the air bearing inbuilt. Other class is also, you can see here, these are porous air bearings, and there is one company which is like making these kind of porous bearings, new way bearings from USA. But I think there are a lot of people, a lot of companies now trying to develop this kind of porous air bearings. With respect to the orifice type, is because of the geometry, because of the construction, and these days with the kind of the facilities, the manufacturing capabilities we have, that is also possible to make. So depending on the application, these things can be embedded or can be manufactured separately and can be embedded in the design, and we can use it. So if we broadly classify, what we'll find that there are two type of aerostatic bearings. So one is orifice type, other is porous, and what you see usually is pressurized air is fed through some inlet, and then it passes through. So it just goes in, and then for instance here you can see, and it just bleed through the bearing surfaces and to the atmospheric pressure. And in the porous one, it passes through a porous media, and then yeah, it will simply pass through the bearing surface again. So what we realized, there is a air gap, there is a air film developed, and because of that we are able to get a non-contact bearing surface. But we also need to understand that air film also supports the load, and it also creates a stiffness. So we'll be talking about all those characteristics, and there um, might be some doubt about the application, but once we know the physics and how it works, what we realize that they are very good element and can be used for developing any kind of motion stages, for not only for precision application, for other kinds of system as well. So if we look at it closely, so two things we'll be looking at. One is the load bearing capacity, and the other is the stiffness. So if we look at the load bearing capacity, what we realize that this is for the air bearings and this is for ball bearings, and the stiffness you can see, and what you can see that the in the operating range, of course, the operating range for this kind of air bearings is very small, and within that range, the load bearing capacity is very high, uh, and is way higher than the ball bearing and the stiffness also, if we talk about, the stiffness is also very high. So here the stiffness is also mentioned. So but mind that the working range is really small. Here what we have compared is the porous versus orifice type, and again the stiffness is, you can see here, is very high and is as good as any contact type of bearing. So and how we get it, we'll understand from their characteristic plots. And what we realize that since we have a air gap and air film there, so it can slide very easily. So there is almost no friction, so zero friction. Of course, the viscous drag is there, but again the viscosity of air is very small. So the effective the friction is almost zero. So no friction, so there is no physical contact, so zero wear. It means it's all more or less maintenance free. There will be no wear and tear. Of course, averaging effect is there, so we can have a straighter motion. Very silent and smooth operation. There is no rubbing and there is no hard contact. So there will be no noise. And of course, we can also achieve very high speeds with this kind of systems. So air bearings, if we look at the history and look at the development, this is not something very new and people have been trying. Only thing is it was used for very precise application and restricted to big labs, or I would say for the research only. But as the technology improved and we were able to get different kind of surfaces, the surface requirements, if you are able to achieve the because of the development of new materials, I think now more and more people are using it. So if you look at this is humongous and very big system, and but is on air bearings, and it was developed to mainly characterize the Apollo spacecraft for Apollo mission. What you see here is just a granite block, but the pattern, the groove pattern is scratched and made on the surface, and you can see that air can be fed through, and then through these channels it will develop the pressure and it can glide. So uh, that is beauty of orifice type of bearings, that the entire design can be embedded on the structure itself. And these days any kind of CMM machines you see the or for the semiconductor industry, for the wafer handling, for any kind of precision application, air bearings are must. So the stages we can talk about the gantry type, the XY stages, the coordinate measuring machines, CMM machines we have, the spindles, they are all on air bearings. So when now we look at the applications and the use of these air bearing stages, what we realize that the modern systems, modern machines, they cannot run without these air bearings. So name it coordinate measuring machines. Now in most of the design houses or manufacturing units, they have these units so that they can measure and they can qualify, they can characterize and do the measurements precisely. For making flat panel displays, display systems is everywhere now, and these are used for displays for TVs, for computers. So it's everywhere, and the manufacturing, the yield, the kind of things required is again is very high. Of course, the semiconductor industry, the lithography, wafer inspection, these kind of systems required for manufacturing chips is needed. Uh, for automation, robotics, and automation applications. Of course, we are now looking for very high precision applications, and we don't want to compromise on the yield. Therefore, we can see these air bearing stages these days. Metrology, machine tools, any kind of optical applications, it's everywhere. So, I think knowing these elements and what is the basis, how to design these air bearing stages using the individual component, at the same time understanding the working principle of these air bearings will lead us to design these kind of systems for our own applications and to support the industries here. So, we can see that so new way is a Nelson Air. So, it's from the website, and what we can see is any kind of motions if you want to have, you can get this kind of elements. So, for instance, planar X, Y, and rotary motions. Here you have even journal bearing, air bushings. So, it can you can have a rectangular air bearing as well. So, it can be embedded on all the sides, and it can slide easily. Different arrangements we can get dovetail air bearing. So, for rotary table applications, so you want to have rotary motions only and very high axial load. So, we can create that kind of interfaces, spherical air bearings, or even the spindles. So, in all these applications, what we see that there is no direct contact, there is no physical contact between the moving parts, they are floating. And since there is no friction, the maintenance, the wear and tear, that we can eliminate, and the operation is very quiet, and at the same time the precision level is very high. So, we need to understand how it works, and so that we can understand, and we also try to use these elements for our own applications. So, this is some work I did while working in Singapore. So, it's so what we did is for a RFS type, how it works, and try to understand the physics of it, and then try to define the design guidelines. Of course, it has been used, but um, uh, very few literature available in open domain. Mostly it was owned by the companies, and of course, it's a good for their uh, commercial interests that people should not know. But at the same time, the academia, the research institute, they want to develop this capability so that the more people can use it, and the adoption of technology can be widespread, and everybody should be able to use it. So the purpose was to understand, and then uh, what are the various parameters, how the different mechanical properties, mechanical behavior depends on certain parameters. So, orifice type of air bearings, very easy to use, and easy to understand as well. So, here what we have is pressurized air fed. So, here maybe what we can see is there is inlet pressure, and there is a pocket inside, and then here we have a groove, central pocket, and then there is a restrictor here, and then air is passed through. So what you see here in the first diagram is air is fed through and W is the initial load, suppose. So once air is fed, there is a restrictor and there is a pocket here, and then okay, along the bearing surface the air will just bleed through. So what happened, because of the fluid dynamics, there will be pressure developed. So inside the pocket there will be some pressure developed, PD, which might be less than the supply pressure. So because there is a restrictor, but that pocket is bigger than the bearing surface. So of course the air pressure will be same, so it will be PD, and then there will be along the surface there will be pressure distribution, so pressure will change, and then at the outside is the atmospheric pressure you have, so from PA to PD. What you realize that when we just integrate this pressure over area, will get the overall load. So what happens if there is any external load applied? So now refer to figure 2. How it supports the load, that dynamic load, any load, any change in the load, how it's getting supported. So what happens moment there is some external load, it will try to press, and so the pressure distribution will change. So it will, PD will change to PD dash, and then there will be again new pressure distribution. And if we just try to find the area and over the area P versus dA, we will find that this overall force is the pad, and this area, the pressure versus dA, if we integrate, what we will find that this will take care of this W as well as any external load. So by redistributing, by changing this pressure, is able to accommodate any kind of load. Now the question is how much it can, and one can also argue that okay, if there is very some force applied, a large force applied, maybe it will crush. So that's something we wanted to learn and understand, and therefore we carried out this study. What we also need to understand that what is the working range, what is the air gap we are talking about when we are talking about these kind of systems. So it's just a comparison here. So typical bearing clearance and tolerance versus this is the human hair we are talking about, this big circle, black one. If this is a size of the human hair, the diameter, which is of the order of 70-80 micron. This is the human cell, the green one, 20 micron. The finer dust particle we are talking about 4 micron, that is the size. So now this gap is of the order of 5 to 20 micron. But to be very precise and want to work with these porous air pads or porous air bearings, it will be of the order of 4 to 5 micron. So we are working in this range, 5 micron range, not even 20 micron. So if we are working in that range, 5 micron range, that is the gap we are talking about. Now imagine the flatness, the requirement, flatness requirement of the surfaces. At least if this is my gap, if I'm talking about, then the flatness requirement should be maybe at least 1/10. So the surface requirement, the flatness, may be of the order of below 1 micron we are talking about. So, we should be aware of that. At the same time, dust particle is of the order of 4 micron. It means the air which is passing through those bearing surfaces, it has to be prepared. It has to be dust free. So, the filtering is required. mm. So, you cannot feed any kind of air. So, of course, the pressure, the supply pressure, what is the effect of the supply pressure? The air quality, the dust, amount of dust is a no. At the same time, any kind of oil is also not good because it will clog the surfaces. So, those are the requirements, and I think once if we want to use this, we should be aware of that. What we also need to understand that this is fed to the orifices and then it will simply pass through the bearing surface and then to the atmospheric pressure. So, it is always a positive pressure most of the time unless we are using some kind of vacuum preloading. So, we will talk about preloading. So, what happens that it always purges. So, it cleans the bearing surface, so which is good. So, there are a lot of positive, but at the same time we also need to understand the requirement and we have to design using those kind of elements and using those assumptions. So, all kind of air bearings can be classified. So, a lot of work done at different places by different people. So, you can see slot, orifice, porous. So, some devices also fluidic inherent. So, inherent means yeah, because of the pockets, because of those designs, uh, the squeeze film, those things can be we can get and we can create bearing surfaces, and we can also uh, have a elastic component embedded. So, we can get aero aeroelastic kind of behavior. Even the air bearing or the air film, they have also elasticity, and how we can make use of those kind of phenomena, I think is very interesting. And at the same time, one has to really understand how it works. And of course, you have parallel surfaces, conical, we can have groove or even membrane. So, different kind of uh, bearing configurations. We can also see that compared to what we use on daily basis in the manufacturing shops or in the machine tools, we can also mimic those kind of uh, movement, and we can have air bearing counterparts. So, like externally pressurized. So, here of course, we have the pressurized air fed, but it can be self acting because of the dynamics also we create. So, just like journal bearing. So, and it's a tilted. So, because of the movement also pressure is created and we can support. So, flat, it can be annular, journal, even conical and spherical and even compliant. So, we can classify, and depending on the application it can be redesigned and we can get a different configurations. So, orifice type is very common, and what you see here are different kind of orifices, and this one is just a single orifice at the center, what you can notice, and then that is the bearing surface. So, it's just uh, air pressurized air will come through that center hole and then just come out of that bearing surface. In the B, there is a central pocket. So, it just first comes to the pocket and then it will come through the bearing surface. Here again. There are annular type also. So it's not fed at the center, but in the annulus in the on the side, and then you have a groove pattern. So it flows inside and it flows out also. So there is a annular type and there is a annular groove. So air is fed through a hole to the groove, and then from the groove it will flow through the bearing surface. We can have a combination. So central pocket, and then we have the orifices, annular and the central. It can have a rectangular shape also for the we can put on the sides, on the surfaces. So not necessarily it has to be a circular, it can be rectangular, but it can be also used for rotary application, for journal application. So similar kind of orifices and the grooves or the pockets can be done and can be analyzed. So there is a lot of freedom, and the designer has a choice what kind of elements, what kind of patterns to be used, so that we can maximize the performance. And here we might be looking at two performances, two characteristics. One is the load capacity, the bearing load capacity, and the stiffness without crushing. So what is the maximum stiffness we can achieve? What is the bearing load it can take? I think that is the key criteria while designing this kind of system. So what we did is simply we take this case, the orifice type with the central pocket, and what you see is that there is a pocket here. So air is passed through. So first comes here, and then again it passes through the bearing surface. So it is going like this, and this is atmospheric pressure, and we just learned how it supports the load. So there is one restriction here, flow through the orifice, and there is another one which is flow through the bearing surfaces. So there are restrictions on the flow, and this is how it works, and it builds up the pressure so that we get a pressure distribution over the bearing surface area, and that's how it supports the load. And when there is any fluctuation in the load, any dynamic load acting, how these restrictions, these restrictors play a role, I think that is the key to understand the working principle of these air bearings. So we'll try to understand this part in little detail, and also try to understand how we calculate the load bearing capacity and how the stiffness changes. And of course, this is a very basic element, but there are a lot of developments and a lot of designs can be proposed and made, and we can design these things on the surface of the bearing surface itself, and we can get these things lifted, and there will be no contact when things are moving. So there will be no contact bearings, no friction, zero friction, so maintenance free, no backlash associated with the friction and the stiffness. So since no friction, so we can say there is no hysteresis, and therefore it's easy to achieve higher precision and repeatability. So we'll continue, and we'll stop here today. Thank you.